January 1942. The Midwest winter bites into the steel skeletons of American factories. Steam hisses from boilers. The scent of oil and molten metal hangs in the air. Workers, men and women drafted from towns, farms, and cities, move with precise urgency along assembly lines that groan under the weight of engines, aircraft parts, and military machinery. The war is no longer distant. Pearl Harbor has thrown the United States into the conflict, and every day counts. Yet the rhythm of production is uneven. Machines clatter, but human hands struggle to keep pace. Skilled labor is scarce, bottlenecks form, and precision is difficult to maintain. The nation's industrial heart beats fast, but is labor-bound, flawed, and desperately in need of innovation. Amid this urgency, engineers at the Bendix Corporation in South Bend, Indiana, are quietly sketching a future no one has fully imagined. Electromechanical machines, designed to calculate, measure, and control production processes automatically, stand at the threshold of reality. They promise speed, precision, and scale, qualities the war demands, but America has yet to master. In the frozen dawn of 1942, the first stirrings of industrial automation begin to hum. The factory floor is about to change forever. December 7th, 1941. The morning sun had barely risen over Pearl Harbor when the quiet harbor erupted into fire and smoke. Japanese bombers tore through the sky, striking battleships, cruisers, and airfields. America, long insulated from global conflict, was suddenly at war. Within hours, the nation's industrial machine, still rooted in peacetime, shifted into overdrive. Factories that had produced automobiles, typewriters, and radios were now pressed to build tanks, aircraft, engines, and ordnance. The stakes could not have been higher. Across the United States, cities like Detroit, Chicago, Cleveland, and South Bend transformed almost overnight. Streets buzzed with trucks delivering raw steel, aluminum, and copper. Rail cars carried engines to assembly lines that had been retooled in haste. Yet the challenge was immediate. American factories were fundamentally manual. Assembly relied on skilled laborers, hand tools, and human calculation. Production lines were designed for peacetime volumes. Wartime urgency exposed the inefficiencies. Bottlenecks slowed output, errors crept in, and the pressure on the workforce was relentless. At the same time, the Axis powers, Germany, Italy, and Japan, were exploiting industrial innovation to devastating effect. German factories were experimenting with mechanized assembly, precision stamping, and standardized components. Britain, under constant threat from Luftwaffe bombing, relied on mass production techniques honed during World War I, but combined with new, semi-automated systems. America, despite its immense resources, lagged in the specialized, high-speed production of complex military machinery. It was in this context that the Bendix Corporation entered the scene. Founded in 1924 in South Bend, Indiana, Bendix had earned a reputation for automotive and aviation components, including brakes, carburetors, and early aircraft instrumentation. Their engineers were accustomed to precision work, but the scale demanded by wartime production was unprecedented. The U.S. military, scrambling to equip forces, placed contracts that required both speed and exacting tolerances, demands impossible to meet with purely manual labor. Bendix's engineers faced a conundrum. How could the nation's factories deliver thousands of high-quality engines, aircraft components, and control systems without exhausting their human workforce or sacrificing precision? The solution, they realized, lay not in adding more hands, but in mechanizing thought itself. Electromechanical systems, guided by punch cards and early computational logic, could automate repetitive tasks with far greater accuracy. These were not computers in the modern sense. They could not store programs or execute complex algorithms, but they could perform calculations, measure tolerances, and coordinate assembly steps far faster than any human. Yet challenges loomed. Manufacturing machines of this kind were untested on the scale required. Components had to be reliable in harsh factory environments, and operators had to be trained quickly, often while the machines were still in prototype stages. Supply chains for precision parts were fragile. Any delay could halt an entire production line. And above all, the pressure of war allowed no margin for error. Military contracts were strict, deadlines were tight, and the consequences of failure could ripple from the Midwest all the way to the Pacific and European fronts. Despite these obstacles, the potential of automation was undeniable. Early experiments with semi-automated processes, mechanical timers, motorized conveyors, and measurement gauges showed promising results. Bendix engineers sketched designs for machines that could control entire assembly operations, from engine block machining to final inspection, reducing the reliance on manual calculation and repetitive labor. The idea was radical. Let machines perform the precision work humans struggled to sustain over long hours. By January 1942, as snow blanketed the Midwest, the urgency of war combined with the promise of automation. American factories were a crucible of innovation, fueled by necessity, expertise, and a willingness to experiment. Bendix stood at the edge of this transformation. The era of purely manual production was ending. What lay ahead would not just change factories, it would redefine the very mechanics of war production. By early 1942, the war was escalating on multiple fronts. In Europe, German panzer divisions rolled across the Soviet Union in Operation Barbarossa. In the Pacific, Japanese forces pressed in Southeast Asia and the Philippines. Every theater of war demanded a continuous, reliable flow of American-made machinery: aircraft engines, bombers, naval guns, and tanks. The United States' industrial advantage, its vast factories and natural resources, was unquestioned, yet the ability to transform raw steel and aluminum into complex weaponry at scale was limited by human speed. Bendix engineers recognized the magnitude of the task. Their work on automotive and aviation components had taught them the importance of precision, tolerances, and repeatable processes. But mass-producing components like aircraft carburetors, gyroscopes, and engine blocks with minimal error was a challenge that could no longer rely solely on skilled labor. Every deviation risked catastrophic consequences in combat, and the manual inspection and measurement of thousands of components consumed time the war did not allow. The solution lay in mechanization, and not just in the crude sense of powered tools. Bendix envisioned machines capable of controlling sequences of operations automatically, using cams, relays, and early forms of computation to dictate every movement. These electromechanical systems could measure, align, and assemble components with precision previously attainable only by the most experienced craftsmen. The machines were designed to operate tirelessly, without fatigue, and with a repeatability that human workers could not sustain over long shifts. Government contracts accelerated the effort. The U.S. Army Air Forces and Navy began investing in these experimental systems, recognizing that the scale of production required a technological leap. In South Bend, Bendix engineers transformed large factory floors into laboratories of innovation. Motors hummed, conveyor belts crawled forward with measured rhythm, and rows of machines awaited programming via punched cards and relay logic. Each machine represented a bridge between human ingenuity and mechanical execution, a hybrid of skill and automation tailored to wartime needs. But implementation was far from simple. Components had to withstand industrial vibration, temperature extremes, and the shock of continuous operation. Maintenance crews needed new training. Workers had to learn to coordinate with machines that operated at speeds faster than human reaction times. Bendix engineers iterated tirelessly, testing, adjusting, and refining to ensure reliability. Failure was not just an inconvenience. A single misalignment in an engine block or a miscut gear could compromise an entire aircraft or vehicle destined for battle. Meanwhile, the urgency of the global conflict provided both pressure and opportunity. Germany had advanced mechanization in factories supporting its Luftwaffe and Panzer divisions, and intelligence reports suggested that American forces needed to match or surpass these capabilities quickly. Britain's experiences during the Blitz had shown the value of semi-automated assembly in maintaining output despite bombing disruptions. The United States, armed with vast natural resources and a skilled engineering workforce, now faced the question: could it convert potential into tangible results in months, not years? By mid-1942, Bendix had developed prototypes capable of performing key manufacturing operations automatically. Machines could control drilling depth, regulate metal cutting, and assemble subcomponents with minimal human intervention. Operators were required, but their roles shifted from hands-on labor to machine supervision, quality control, and troubleshooting. Factories became hybrid ecosystems where humans and machines worked in tandem. The rhythm of production governed as much by relay logic as by human coordination. These early automated systems did more than increase speed. They introduced a level of consistency essential to wartime production. Each part conformed to exact specifications, reducing failures in the field and increasing the reliability of aircraft engines, carburetors, and other critical components. For the first time, the U.S. could approach the scale of output demanded by global conflict without sacrificing the precision that combat machinery required. As 1942 progressed, it became clear that Bendix's work was not merely a technical experiment. It was a turning point. The integration of automation into American factories offered a glimpse of a new industrial age, one where computation, machines, and human oversight combined to achieve results previously unattainable. The war was shaping not just weapons and strategies, but the very mechanics of production itself. Inside the Bendix factories, the human element remained central. Workers in overalls, faces streaked with soot and sweat, circled machines that clicked, whirred, and hummed with newfound intelligence. For many, this was unfamiliar territory. The factory had always demanded skilled hands and steady nerves, but now they had to interact with machines that operated faster than human reflexes. The role of the worker shifted, no longer simply shaping metal or turning wrenches. They became overseers, problem solvers, and coordinators. Women, who had entered industrial labor in unprecedented numbers after the men went to war, played a crucial role. Their meticulous attention to detail ensured that early automated processes ran smoothly. Even minor misalignments could halt a line, and the human eye and hand remained vital for correction. The machines did the calculations, but humans interpreted the results, adjusted the levers, and maintained the flow. Morale was a delicate balance. Pride in working at the cutting edge, anxiety over the speed of change, and exhaustion from long shifts under high stakes. The psychological impact was profound. Workers had to trust devices that seemed almost alive in their precision. The factory floor became a space of collaboration between man and machine, a partnership forged under the relentless pressure of wartime necessity. Many who witnessed these first automated systems would later describe the experience as both exhilarating and unnerving, the dawn of a new industrial consciousness. Bendix's innovations were a marvel of early automation. Without digital computers, engineers relied on electromechanical devices, relays, cams, gears, and punch cards to control processes with remarkable precision. One machine could measure the depth of drilled holes in engine blocks to thousandths of an inch, then feed the components down a conveyor for the next operation. Another regulated torque on carburetor assemblies, ensuring uniform performance across thousands of units. The brilliance lay in the orchestration. Machines did not operate in isolation. They were networked into coordinated production lines, each step monitored and adjusted automatically. Punch cards acted as primitive programs, instructing machines on sequence, measurement, and timing. Operators loaded cards, checked alignment, and watched the systems execute repetitive tasks flawlessly. In essence, Bendix had created a mechanized brain for the factory, one that could replicate human decision-making in measurement and sequencing, tasks that had previously slowed production. Even small technological breakthroughs had outsized impact. A drill press with automated depth control reduced scrap metal and rework. A precision conveyor system eliminated bottlenecks in assembly. Accuracy and consistency improved, not just speed. And perhaps most importantly, the system scaled. Each machine added to the line multiplied efficiency, creating a compounding effect on production output. The implications for the war effort were immediate. Every engine completed, every aircraft component manufactured with precision, translated directly into battlefield capability. The U.S. Army Air Forces could equip squadrons faster. The Navy received ships' components on tighter schedules. Automation allowed production to meet not only quantity but quality standards, a factor often overlooked in conventional discussions of wartime output. Bendix's systems were particularly valuable for aircraft engines. Previously, inconsistencies in machining could lead to failures in flight, jeopardizing both missions and lives. Automated processes standardized every component, ensuring engines were interchangeable and reliable. This meant squadrons could be deployed rapidly, repairs could be made with confidence, and losses due to mechanical failure were minimized. Strategically, the introduction of automated lines shifted the U.S. industrial posture. Where previously manpower and time constrained production, technology now created leverage. Factories could produce at scales that rivaled and eventually surpassed German and Japanese capabilities. In effect, Bendix's work transformed the domestic industrial front into a tactical asset, where speed, precision, and reliability directly influenced operational success overseas. At the heart of Bendix's automated revolution were the engineers and executives steering the effort. Leaders like Vincent Bendix, the company's founder, and key engineering managers understood that innovation under wartime pressure required both vision and decisiveness. Decisions that might have taken months in peacetime had to be made in days, and mistakes carried real consequences, not just financial, but strategic. The management style combined methodical planning with rapid prototyping. Engineers were encouraged to experiment, yet rigor and documentation were non-negotiable. Each machine, relay, and assembly line layout was tested against tolerances stricter than civilian standards. Military liaisons visited the plant frequently, demanding updates and modifications to meet evolving specifications. Leadership had to balance speed, precision, and worker morale, guiding a workforce unfamiliar with electromechanical systems into a new era of production. Perhaps most crucially, Bendix leadership recognized that automation was more than technology. It was an organizational transformation. They restructured teams, redefining roles from hands-on assembly to machine supervision, and invested in training programs to ensure that humans and machines could operate seamlessly together. The result was a culture that merged ingenuity, discipline, and foresight, creating a workforce capable of meeting the unprecedented demands of global war. Across the Atlantic, German intelligence monitored American industrial expansion with a mixture of curiosity and alarm. Reports indicated that U.S. factories were producing aircraft and engines at an accelerating pace, a tempo difficult to reconcile with traditional labor-intensive methods. While Axis spies could not observe Bendix machines directly, the impact was evident. American production numbers were rising, and Allied air power was beginning to dominate contested skies. Germany had pioneered some automated processes in munitions factories, but its application in complex engine production lagged behind the evolving U.S. methods. Military planners in Berlin recognized that if the Americans could combine reliability with speed, Axis forces would face a strategic disadvantage not just on the battlefield, but in the logistics of sustaining prolonged conflict. Bendix's semi-automated systems, though invisible to enemy eyes, were already shaping the broader calculus of the war. Production was no longer just a domestic concern. It was a tactical weapon in itself, one whose effects would be felt far from the factory floor. The shift toward automation also raised questions on the home front. Machines that could perform skilled labor with higher consistency and speed threatened to displace workers, even as the wartime economy demanded more hands. While women and previously underrepresented labor groups found opportunities in factories, there was a subtle tension between human effort and mechanical efficiency. Society had to reconcile progress with consequence. Labor unions debated whether machines would erode worker power or create new roles demanding greater technical skill. Engineers and managers faced ethical considerations. The push for speed could not come at the expense of safety. Accidents were real, and overworked operators could falter under pressure. Yet the broader moral imperative, winning the war, often outweighed individual concerns. The human cost was acknowledged but measured against the national stakes, a tension familiar in any society adapting to rapid technological change. Bendix's automation ultimately symbolized a crossroads, the promise of efficiency, precision, and mass production on one side, and the challenge of human adaptation, workforce displacement, and social change on the other. The factory floor became a microcosm of the broader societal shift. The integration of human skill and machine capability under extreme necessity. By mid-1942, Bendix's automated systems had moved beyond prototypes. Factory floors in South Bend and other Midwestern plants were transformed. Machines, guided by relays, cams, and punch cards, moved with relentless precision. Drill presses, lathes, and assembly conveyors synchronized like a symphony. Every cut, every alignment, every inspection executed automatically, without pause or fatigue. For the first time, human hands were no longer the limiting factor in production. Machines dictated the pace, while humans guided, corrected, and ensured quality. One of the first major successes was in the production of aircraft carburetors, a critical component for engines that powered B-17 bombers and other frontline aircraft. Previously, each carburetor required careful attention by skilled machinists, with tolerances measured in thousandths of an inch. Errors were frequent, and production rates lagged behind military requirements. The Bendix automated system transformed the process. Machines drilled, milled, and assembled components at a rate that outstripped human capability. Quality improved while throughput increased. Inspectors reported dramatically fewer defects. Production lines that once yielded hundreds per week now produce thousands, all ready for deployment. The tempo of change was staggering. In engine assembly, electromechanical control units monitored torque, alignment, and timing. Components fed themselves down lines with minimal human intervention, each stage tracked by primitive computing systems that measured and adjusted automatically. Factory supervisors watched in awe as machines executed tasks that had previously consumed hours in mere minutes. Operators became coordinators, not laborers, interpreting signals, correcting minor misalignments, and maintaining flow. The rhythm of production had been rewritten. Military officials began to notice. Representatives from the U.S. Army Air Forces toured Bendix factories, observing the speed and accuracy of the automated lines. Reports from January to June 1942 documented the improvements. Engine production schedules were accelerating, defects had dropped sharply, and turnaround times from raw material to finished assembly had been cut in half. The military began allocating additional contracts and resources to expand the initiative. Bendix's success was no longer a laboratory experiment. It was an operational advantage with immediate strategic impact. The first fully automated or semi-automated production line was not without tension. Early days saw misfeeds, jammed punch cards, and misaligned components. Engineers worked around the clock, making rapid adjustments, reinforcing the fragile lines between success and failure. Every machine had to be calibrated precisely, every relay timed perfectly. A single misstep could halt thousands of parts, threatening schedules and contracts. Yet, as the weeks progressed, the system stabilized. Lines ran with remarkable consistency, the machines almost seeming to think as they performed the work of hundreds of human hands. By summer 1942, the results were unmistakable. Carburetors, engine blocks, and critical subassemblies emerged from Bendix lines faster and with higher precision than ever before. Human supervisors marveled at the pace. Production figures exceeded projections. This was a turning point not just for Bendix, but for wartime manufacturing in the United States. For the first time, automation allowed the nation to scale production without sacrificing quality, a decisive advantage in a conflict where every plane, every engine, and every part could influence the outcome on distant battlefields. The factory floors, once a theater of human endurance, had become a hybrid ecosystem. Humans and machines operating in tandem, the latter amplifying the skills, speed, and reliability of the former. For the engineers who had dreamed of semi-automated systems, the moment was electrifying. The vision of machines executing precise operations automatically, once theoretical, was now manifest. The tempo of American war production had accelerated beyond conventional limits. By late 1942, Bendix's automated systems had moved from pilot lines to full-scale production. Entire engine assembly floors now operated with unprecedented synchronization. Conveyor belts carried components with flawless timing. Machines measured, aligned, and joined parts with the precision of a master craftsman, but faster and tirelessly. Human oversight remained essential, yet the balance of labor had shifted decisively. Humans no longer performed repetitive calculations or measurements, but monitored, adjusted, and optimized. The first major operational milestone came in the production of Pratt & Whitney R 1830 twin Wasp engines, vital for B-17 Flying Fortresses. Previously, production of these engines was a slow, meticulous process. Any misalignment or error could ground a bomber, endangering air crews and missions. Bendix's automated lines transformed the task. Machines drilled cylinder heads, calibrated fuel systems, and aligned pistons with minimal human intervention. Output doubled, defects dropped sharply, and each engine could be traced through every stage of production with meticulous records, ensuring reliability at scale. Inspectors who had once spent hours measuring components found themselves supervising dozens of machines simultaneously, marveling at their consistency. The military impact was immediate. By December 1942, B-17 squadrons were receiving engines faster than anticipated, allowing more bombers to reach combat zones in Europe and North Africa. Logistics officers noted that maintenance cycles shortened because engines produced with automated precision required fewer repairs. Commanders realized that speed and quality on the production line translated directly into tactical flexibility in the field. Air missions could be launched with confidence, and aircraft losses due to mechanical failure diminished. This period also highlighted the adaptability of Bendix engineers. Machines initially designed for small subassemblies were repurposed for complex tasks. Carburetor assemblies, gyroscopic components for navigation instruments, and fuel system parts. Electromechanical controllers coordinated sequences across multiple machines, creating assembly chains that functioned as cohesive, self-regulating systems. The factory became an organism, each machine a vital organ, each human supervisor the nervous system maintaining balance. The broader strategic picture became clearer. Automation was no longer an experimental adjunct. It had become a force multiplier. Bendix's successes sent ripples through the U.S. defense establishment. Government officials visited factories, observing production lines that moved at speeds unimaginable a year prior. Reports highlighted the potential. If these methods could be implemented nationwide, the U.S. could outproduce Axis powers in critical equipment, gaining a decisive advantage in material resources. Yet challenges persisted. Early systems required constant calibration. Parts tolerances were exacting, and any deviation could halt the line. Operators had to be trained quickly, often while the machines were in operation. Engineers worked in 12-hour shifts, tweaking cams, relays, and motors, ensuring uninterrupted flow. Despite fatigue and pressure, the results spoke for themselves. By the end of 1942, Bendix lines had become the gold standard for semi-automated manufacturing. The emotional resonance on the factory floor was palpable. Workers, initially anxious about machines replacing human labor, began to see themselves as partners in a new industrial frontier. Pride replaced trepidation as the magnitude of what they were producing became clear. Engines, carburetors, and instruments that would fly over battlefields, power tanks, and support troops halfway across the globe. Human skill and mechanical precision were intertwined, each amplifying the other, both serving the nation's urgent needs. In the span of a single year, Bendix had demonstrated the transformative potential of automation. What had begun as sketches on drafting tables and experimental rigs had evolved into fully operational production systems, capable of delivering high volumes of complex machinery with unprecedented reliability. American industrial power, once constrained by human limitations, had been expanded through innovation and necessity. By early 1943, the results of Bendix's automated production systems were undeniable. Factory floors that had once struggled to meet quotas now operated with relentless efficiency. Engines, carburetors, and precision components rolled off assembly lines at speeds previously unimaginable. The U.S. Army Air Forces and Navy noted immediate improvements. Aircraft were equipped faster, mechanical failures in the field declined, and mission readiness increased. The American war machine had gained a new, decisive advantage. not just in manpower, but in the quality and consistency of its industrial output. Production statistics painted a clear picture. A single Bendix line producing carburetors could now manufacture thousands per month, whereas manual assembly had previously yielded only a fraction of that number. Engine assembly timelines were halved. Inspectors reported defect rates dropping by 40 to 50%. Each component was traceable from raw material to final assembly, allowing maintenance crews to anticipate and prevent failures. These figures, meticulously documented in military reports, demonstrated that automation had become more than a laboratory experiment. It was a strategic instrument. The human impact was equally significant. Operators, once apprehensive about machines replacing their work, began to embrace their new roles as supervisors and problem solvers. Skilled labor was not eliminated but redefined. Workers developed technical expertise in maintaining and coordinating electromechanical systems, a skill set that would prove invaluable both during and after the war. The factory floor had become a partnership between man and machine, one that combined speed, precision, and oversight in ways previously unattainable. The military response was immediate and enthusiastic. Bendix lines were prioritized for expansion, and additional contracts flowed into scale automated production across the Midwest. Government reports emphasized not only output but reliability. Aircraft engines produced via automated processes performed consistently in combat, reducing losses due to mechanical failure. The impact was tangible in theaters from North Africa to the Pacific, where faster delivery of reliable engines and components directly influenced operational capability. Beyond numbers, the psychological effect was profound. Military leaders, engineers, and factory supervisors recognized that automation had fundamentally altered the industrial landscape. American production was no longer constrained by human endurance or the limitations of manual calculation. The Bendix systems demonstrated that precision, speed, and reliability could coexist, setting a benchmark for future industrial innovation. By mid-1943, the ripple effects of Bendix's automation were evident beyond South Bend. Factories across the Midwest began adopting similar systems, inspired by Bendix's success. Military contracts emphasized the need for standardized, reliable production, and automated or semi-automated lines became a benchmark for efficiency. Aircraft engines, carburetors, and critical ordnance components flowed steadily to training bases, airfields, and front lines overseas. The United States was beginning to realize the full scale of its industrial potential, unhindered by human bottlenecks or inconsistent manual production. The labor force adapted rapidly. Workers learned to maintain, calibrate, and troubleshoot electromechanical machines, transitioning from traditional assembly tasks to technical oversight. Training programs multiplied, equipping employees with knowledge in precision measurement, relay logic, and process management. For women and previously underrepresented groups, these new roles offered unprecedented opportunity. Automation did not eliminate jobs entirely. It transformed them, creating a workforce skilled in emerging industrial technologies. Strategically, the consequences were profound. In Europe, U.S. bombers reached squadrons faster than German intelligence anticipated, giving Allied forces critical momentum. In the Pacific, reliable engines allowed more aircraft to support island-hopping campaigns and carrier operations. Bendix's machines were silent contributors to victories, their impact often invisible, yet measurable in mission success and operational readiness. Military reports from late 1943 highlighted reductions in mechanical failures and noted the reliability of mass-produced parts, a direct outcome of automated processes. The long-term industrial implications were even more significant. Bendix had demonstrated that complex mechanical systems could be produced consistently and at scale without relying solely on human skill. Post-war, the principles of automation would spread into peacetime industry, automobile manufacturing, appliance production, and eventually computer-aided systems. The company's work foreshadowed the modern assembly line, where human ingenuity guided machines capable of executing precise tasks with minimal supervision. Yet there were challenges. Early automation required constant maintenance and expert oversight. Machines could not replace critical thinking or adaptability. Humans remained essential for problem-solving and quality control. There were debates over workforce displacement and social consequences, particularly as industries considered expanding automation into civilian manufacturing. However, the wartime urgency provided a compelling argument. Machines multiplied human capacity, reduced errors, and accelerated production to levels necessary to win a global conflict. By the end of 1943, the results were unmistakable. Bendix's automated systems had transformed the American industrial landscape, increasing efficiency, reliability, and production speed. Factories hummed with a new rhythm, a hybrid of human skill and mechanical precision that would define wartime manufacturing. The company's innovations did not merely meet the immediate demands of war. They laid the foundation for decades of technological advancement, demonstrating that necessity, ingenuity, and mechanization could together achieve results once thought impossible. By the end of 1943, the significance of Bendix's automated systems extended far beyond factory floors. These machines had done more than accelerate production. They had redefined the relationship between humans and technology. Skilled labor was no longer measured solely by physical endurance or repetitive precision, but by the ability to orchestrate and supervise complex systems. The factory became a space where ingenuity and machine capability intertwined, each amplifying the other. In the broader context of World War II, Bendix's innovation exemplified how necessity drives invention. America faced a global conflict on multiple fronts, with immense pressure to deliver quality war material at unprecedented speed. Automation offered a solution, not by replacing human skill, but by harnessing it. Every engine produced, every precision component assembled, directly affected the outcome of battles, campaigns, and the morale of soldiers in distant theaters. The machines, silent and tireless, became instruments of strategic power, turning industrial capability into a decisive wartime advantage. Beyond the war, the implications were profound. Bendix's systems foreshadowed the post-war Industrial Revolution, planting the seeds of computer-aided manufacturing decades before digital computers would dominate production. Factories would never operate the same way again. The balance between human oversight and automated execution, first achieved under wartime urgency, became a model for efficiency, reliability, and innovation in the peacetime economy. There is a human lesson embedded in this history. The story of Bendix reminds us that technology alone is inert. It is the vision, discipline, and adaptability of people that make it transformative. Amid the clamor of machines, the hum of conveyor belts, and the flicker of punch card readers, humans shaped the course of industrial and military history. They bridged imagination and execution, ensuring that necessity became invention, and invention became an enduring legacy. In the winter of 1942, Bendix's automated systems were born from urgency. By the end of the war, they had helped define a new era, a world where human ingenuity and mechanized precision would forever coexist, shaping not only the outcome of conflict, but the very nature of production itself.